Let's talk about the speed of light. You've probably heard it 1,000 times. Nothing can go faster than light. It's one of those facts that gets repeated so often that we stop questioning it. But here's the thing. Most people, even people who've studied physics, don't really understand why this is true. And the usual explanation, the one you hear in most textbooks or science documentaries, actually misses the point entirely. The common story goes something like this. The speed of light is the universe's speed limit. It's like a cosmic speed limit sign posted at 299,792,158 meters per second. You can't go faster because, well, you just can't. Maybe you need more energy. Maybe your spaceship isn't powerful enough. Maybe if we had a better engine, we could get closer and closer, but we'd never quite reach it. That's the story most people walk away with. But that's not what's really happening. And if you think that's what Einstein was saying, you've misunderstood relativity at a pretty fundamental level. So let me ask you a simpler question. What do we even mean when we say something is moving fast? You're probably thinking, well, it's covering a lot of distance in a short amount of time. That's what speed is, right? Distance divided by time. Simple. Except, what is distance and what is time? Now, hold on. I'm not trying to be philosophical here. I'm asking a physical question, because it turns out distance and time are not the fixed, absolute things we thought they were. And once you really understand that, the whole speed of light limit thing stops being a mystery and starts making perfect sense. Here's where most people go wrong. They think space is this big empty stage, and time is this universal clock ticking in the background, and objects move around on the stage while the clock ticks. That's the Newtonian picture. It's intuitive. It matches our everyday experience, and it's completely wrong. Einstein didn't just tweak Newton's laws. He showed that space and time aren't separate things at all. They're woven together into a single fabric called space-time. And here's the weird part. How much of your motion goes through space versus how much goes through time depends on how fast you're moving. You're always moving through space-time at a constant rate, but you can trade motion through space for motion through time, and vice versa. Let me try to make this more concrete. Right now, as you're sitting here reading this, you're moving through time at a certain rate, 1 second per second, we'd say, but you're barely moving through space. Maybe you're sitting still in your chair. So almost all of your motion through space-time is in the time direction. Now imagine you start moving. You get up, you walk, you run, you get in a car. As you start moving through space faster and faster, something strange happens. Your motion through time slows down. Not in some metaphorical sense. Literally, physically, measurably slows down. Clocks that are moving relative to you actually tick slower. Time itself passes more slowly for you. This isn't science fiction. This is real. We've measured it. GPS satellites have to account for this effect, or they'd give you the wrong location within minutes. Particles in accelerators live longer than they should because they're moving so fast that time slows down for them. This is as real as gravity. So here's the key insight. You're always moving through space-time at a fixed total speed. Think of it like this. Imagine you're driving a car and your speedometer is broken, so it always reads exactly 100 kilometers per hour, no matter what. But you can change direction. You can go north, south, east, west, or any combination. If you're going purely north at 100 km/h, you're not going east at all. If you turn slightly east, you're now going, say, 70 km/h north and 70 km/h east. The total speed stays the same. You're just redistributing it between directions. Space-time works the same way. You're always moving through space-time at a fixed speed. Let's call it Sichtson, the speed of light. Right now, almost all of that motion is through time. But as you start moving through space, you start using up some of that motion. The faster you move through space, the slower you move through time, because your total motion through space-time has to stay constant. Now, what happens if you try to put all of your motion into space? What if you tried to move through space at speed? Using up all your motion. Well, that would mean you'd have zero motion left for time. Time would stop entirely for you. You wouldn't age. You wouldn't experience anything. From your perspective, you'd leave one point and instantly arrive at another, no matter how far apart they were. There would be no journey. No time would pass. And that's exactly what happens for light. Photons, particles of light, move through space at speed, c gain. And for them, no time passes at all. A photon that left a distant star 1 billion years ago, from our perspective, experienced exactly 0 time. It was emitted and absorbed in the same instant from its own non-existent perspective. So now we can start to see why nothing with mass can reach the speed of light. It's not because you need infinite energy, though that's true, and we'll get to that. It's because if you were moving at the speed of light, you would experience no time at all. And if you don't experience time, you can't be a thing that exists in the normal sense. You can't have thoughts. You can't have internal processes. You can't change. You're frozen, not in space, but in time itself. But wait, you might say, what if I just kept accelerating? What if I kept pushing harder and harder? Surely I'd eventually reach the speed of light. Here's where it gets even weirder. From your perspective, in your own reference frame, you absolutely can keep accelerating forever. You can fire your rocket engines as long as you want. You'll feel the acceleration. You'll watch distant stars start moving past you faster and faster. There's no subjective speed limit from your point of view. But here's the thing. As you get faster, time dilation kicks in. Your clocks slow down relative to the outside universe, and length contraction happens. Distances in the direction you're traveling get shorter. From your perspective, the galaxy might shrink to just a few light years across. You could cross it in what feels like a few years of your own time. But to an outside observer, something different is happening. They see your clock slowing down. They see you getting heavier, not in the sense that you're gaining matter, but in the sense that your inertia increases. It takes more and more force to accelerate you by the same amount. The closer you get to the speed of light, the more energy it takes to push you even a tiny bit faster. And it's not because your rocket is weak. It's because mass and energy are related. I, Rho, MC2. And as you pump energy into something to make it go faster, you're also increasing its effective mass. The more energy you add, the more inertia you create, and the harder it becomes to accelerate further. So you never actually reach the speed of light. You can get arbitrarily close, 99% of 99.9%, 99.99%, but you'll never quite get there because the energy required approaches infinity. And that's not a practical limitation, it's a structural feature of space-time itself. Now let's pause for a second because I want to address something that confuses a lot of people. You might have heard that the speed of light is constant in all reference frames, that no matter how fast you're moving, if you measure the speed of light, you always get the same answer, c. And that sounds completely insane. How can that be true? Here's the trick. It's true because time and space are not absolute. When you're moving, your rulers shrink and your clocks slow down in just the right way, so that when you measure the speed of light, you always get the same number. This isn't a coincidence. It's the universe maintaining consistency. Imagine you're on a train moving at half the speed of light, and you shine a flashlight forward. Common sense says the light should be moving at 1.5 times the speed of light, right? Half from the train plus 1 full sha from the light itself. But that's not what happens. The light still moves at exactly sikha. Why? Because your time is slowed down and your space has contracted in just the right proportions so that distance divided by time still equals ka. This is what Einstein realized. The speed of light isn't just some random constant. It's the conversion factor between space and time. It's the thing that stitches them together into space-time. Saying nothing can go faster than light is like saying nothing can be more than 100% of something. It's not a speed limit in the usual sense. It's a statement about the structure of reality itself. And here's the really deep part, the part that most people never get to. The speed of light, kukiku, isn't really about light at all. It's about causality. It's about the maximum speed at which cause and effect can propagate through the universe. Light happens to travel at that speed because photons have no mass, so they naturally move at the maximum speed that space-time allows. But kontokes would still exist even if light didn't. It's the speed of causality itself. Think about it this way. If you could send information faster than light, you could send a signal into your own past. You could create causal loops, paradoxes, situations where effects precede their causes. The universe doesn't allow that, not because of some cosmic rule enforcer, but because space-time is structured in such a way that faster-than-light travel is equivalent to time travel into the past. And time travel into the past leads to logical contradictions that simply can't exist in a consistent universe. So when you ask, why can't I go faster than light? The answer isn't because the universe said so. The answer is because if you could, you'd be traveling backward in time, and that breaks causality. The speed of light isn't a speed limit. It's the speed of now. It's the rate at which the present moment propagates through space. Let me give you one more way to think about this, because I think it really drives the point home. Imagine you're trying to go faster and faster. From your own perspective, you're succeeding. You're crossing distances in shorter and shorter amounts of your own time. But from an outside perspective, you're getting closer and closer to the speed of light, which means time is slowing down for you more and more. Eventually, if you could somehow reach the speed of light, time would stop entirely for you. The entire history of the universe, from beginning to end, would pass in zero time from your perspective. You'd exist everywhere along your path simultaneously, with no sense of duration. That's not a state any physical object with mass can be in. It's not that it's hard, it's that it's meaningless. It's like asking what's north of the North Pole. The question itself doesn't make sense once you understand the geometry involved. So the real reason nothing can go faster than light isn't about power or energy or engines. It's about the fundamental geometry of space-time. Time and space are not separate. They're two aspects of the same thing, and the speed of light is the exchange rate between them. Your motion through space-time is always at speed, sec. Right now, you're moving through time at nearly that full speed. If you start moving through space, you trade some of your motion through time for motion through space. The faster you go through space, the slower you go through time, because the total always adds up to c co. And that, I think, is the real answer. It's not a limit, it's a geometry. It's the shape of reality. And once you see it that way, it stops being mysterious and starts being beautiful. There's one more thing I want to leave you with. The fact that we live in a universe where space-time has this structure, where the speed of light is finite and constant, where cause and effect propagate at a maximum speed. That's not arbitrary. It has profound consequences for everything. It's why we have a past and a future. It's why we experience time flowing in one direction. It's why information, memory, and consciousness are even possible. If the universe worked differently, if there were no maximum causal speed, none of this would exist. Not just our technology or our theories, us. The very fact that we're here thinking about this depends on the structure of space-time that makes the speed of light what it is. So when someone asks you, why can't anything go faster than light? Don't say, because Einstein said so. Say, because time and space are woven together, and the speed of light is the rate at which you're always moving through space-time, whether you know it or not.